Right now, strapped to the top of humanity's most advanced multi-billion-dollar rocket, sits a 10-year-old discontinued camera.
Yeah, it's pretty wild.
Right. And if you ask NASA, it's the only tool they actually trust for the job. Welcome to today's deep dive. It is April 1st, 2026, and tonight, the launch window officially opens for Artemis II.
4 astronauts are finally strapping in for a historic 10-day lunar flyby.
Exactly. And our mission today is to figure out why humanity's furthest journey relies on this bizarre mix of, cutting-edge innovation and decade-old retro tech.
It really completely flips our assumption that space travel always demands the bleeding edge.
Okay, let's unpack this camera situation. When the crew shoots the lunar far side, they're completely ignoring modern mirrorless cameras. They're packing 10-year-old Nikon D5 DSLRs instead.
Yeah, what's fascinating here is that a modern mirrorless camera is essentially a complex supercomputer.
Right.
And outside of low Earth orbit, which is that magnetic bubble that protects our planet from space weather, you are just blasted by cosmic radiation.
So it's kind of like taking a trusty, indestructible flip phone on a wilderness survival trip instead of a fragile smartphone.
That is exactly it, because one stray burst of that radiation can instantly fry those complex electronic sensor circuits.
But the older DSLR uses a physical mechanism, right? Like an optical viewfinder and a mechanical mirror.
Right. So a cosmic ray will just pass right through the glass without destroying the camera's brain. It is basically built-in radiation hardening.
That's amazing.
And it has a functional edge, too. It has an extreme ISO range, meaning its light sensitivity pushes to over 3 million.
Wait, 3 million?
Yeah. When the lighting shifts violently between the blinding glare of direct sunlight and the pitch-black void of space, that raw sensor sensitivity handles the massive contrast perfectly.
Okay, so this extreme environment doesn't just dictate the gadgets they bring. It forces their hand on the entire flight path.
If we connect this to the bigger picture, every choice prioritizes fail-safes and passive survival mechanisms over raw power.
Right, like they can't just power their way through space. They have to work with it.
Exactly. We call it a hybrid free return trajectory.
Which basically means if the Orion spacecraft's main engines completely fail out there in the dark, the crew isn't stranded.
No, the physics of the solar system takes over. The moon's gravity catches the spacecraft and naturally slingshots them right back to Earth.
And that same logic applies to getting back through the atmosphere.
Right, because on the uncrewed Artemis I mission, the heat shield suffered some unexpected chunking.
But instead of throwing out the shield design, they're using what's called a skip reentry.
Yeah, it's literally like skipping a stone across a pond.
The capsule bounces off the upper atmosphere to bleed off immense speed before finally plunging into the water.
Which limits the time the spacecraft spends in that peak 3,000-degree thermal environment. It ensures the structure survives without adding tons of heavy extra shielding.
Which makes sense because the same harsh physics dictating that reentry path strictly limits the weight and power they can allocate to life support inside the capsule.
Oh, definitely. They are basically living in a camper van for 10 days.
A camper van with no refrigerator.
Right. They eat thermostabilized meals.
Wait, thermostabilized. So basically high-tech military MREs heated in a briefcase-sized warmer.
Pretty much. And to prevent muscle decay, they obviously don't have room for a massive gym.
Right, so what do?
They use a 14-kilogram flywheel. It's kind of like a giant yo-yo. In microgravity, you don't feel the weight of a dumbbell.
Sure.
But a heavy spinning reel creates inertial resistance. Pulling a cord to spin that mass generates up to 400 pounds of resistance using just the astronaut's own kinetic energy.
Hold on, I have to push back here.
Yeah.
You're telling me we trust 10-year-old mechanical cameras for reliability and a literal spinning yo-yo for exercise, but we can stream 4K video from the moon using the new O2O laser comms. And we're risking the crew's health monitoring on experimental organ-on-a-chip technology.
Oh, no.
Isn't that a massive contradiction?
It sounds like it, but the Avatar experiment actually solves a critical problem. In microgravity, your body stops producing bone cells because it doesn't feel the constant stress of gravity.
Oh, wow.
And bone marrow is also incredibly sensitive to radiation. But we can't exactly do safe, invasive bone marrow biopsies in space.
So instead of poking and prodding the crew, they put the astronauts' actual living bone marrow cells onto tiny, USB-sized synthetic chips.
They do. By flying these biological avatars alongside the crew, scientists measure exactly how radiation affects human tissue at a cellular level in real time.
That is wild.
Yeah, we use cutting-edge tech where it's the only way to get the data and reliable analog tech everywhere else.
So the takeaway for you here isn't just about space, it's the whole concept of passive engineering.
Exactly. True technological mastery isn't about fighting nature with raw power.
Right, it's about designing systems that let the physics of the universe do the heavy lifting for you. The best tool isn't always the newest one.
No, it's the one proven to work when failure just isn't an option.
Which leaves us with this final thought.
Yeah.
If deep space radiation is fundamentally altering the cellular avatars of our astronauts right now,
Right.
will the humans who eventually utilize this technology to settle on Mars biologically evolve into an entirely different species from the rest of us left on Earth?